To reiterate, we've said that you take a big nebulous, a giant gas cloud, collapse it down to gravity, and you get this rotating thing of a protostar surrounded by a protoplanetary disk. And all these properties of what's going to happen to this protoplanetary disk is determined by angular momentum conservation. So let's go ahead and actually define that angular momentum conservation. Momentum is a measure of how much something's moving. It's its product of its mass and its velocity. And the more massive something is, the faster it's going, the greater its momentum. And correspondingly, the greater force necessary to change that momentum. Well, angular momentum is the rotational analog of these momentums. And for whatever reason, we label angular momentum with a L. Don't ask me why. There's a long history there that's just not worth getting into. Just be content to know that here in this section, when I write capital L, I'm referring to the angular momentum of an object. And it is just this straightforward equation with a lot of detail bit into it. L, the angular momentum, is a product. Oops. Let's try that again. The angular momentum is just a product of this I, the moment inertia, and this omega, not W, omega, the angular velocity. Well, there's a lot built into this expression. So let's break this down. What is omega, the angular velocity? It's how rapidly you are rotating around. Take the figure skater who is spinning around, spinning around, spinning around. Angular velocity just says, well, how many rotations in radians per second is this person rotating at? Other terms you'll see associated with this will be the angular frequency. It turns out that our omega is related to frequency. Think of waves when something is oscillating up and down. And angular velocity is very similar to that, just measured in radians per second. For our purposes in this section, just be content to say that this angular velocity is a measure of how fast something's rotating. Now for I, this moment of inertia. What the heck is that? Well, you should be familiar with the phrase inertia. We use it to define the mass, how much something resists changes in motion. So, with that kind of thinking in our brains, the moment of inertia, well, it's a measure of how much an object will resist rotations. Specifically, the moment of inertia is a combination of how massive you are and how that mass is distributed. Think of it this way. Take your bowling ball. Let's see if I can add little dots. There. So there's your bowling ball. And try and get this thing to rotate about an axis. So let's give it an axis to rotate about. And get that thing rotating. So you can just take your bowling ball and just spin, 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 spin. And it's easy. Now take your same bowling ball and let's add, say, a broomstick to it. All right. You've given this thing a broomstick. And now let's try and get this bowling ball rotating about this axis here. All right. Well, now it has this extended mass. Okay. Here, not too bad. This time, this orientation is not too bad. Let's reset. All right. Let's take our bowling ball again. Here's my bowling ball. Let's add the broomstick handle. Now, instead of rotating it about here, let's rotate it here. All right. Same mass, bowling ball with a rod attached to it. But instead of trying to rotate here, where it's easy, you just have this broomstick handle extended from it. Now you're trying to rotate this bowling ball that's way out there, far away from the rotation axis. You're trying to get this swirling thing around. So it is the exact same amount of mass, but you're accounting for how is that mass distributed? Is it close to the rotation axis or is it far away? And that combination of your mass and where your mass is defines your moments of inertia. My last comment about angular momentum on this slide is to say that it is a conserved quantity. If you have a certain amount of angular momentum and you change either the moment of inertia or the angular velocity, in order to conserve angular momentum, one has to change. Remember, when we say conserved quantity, think about things like energy. Energy must be conserved. We have to be able to account for it. Same thing goes for mass. Same thing goes for momentum. Same thing for the angular momentum. Think of the figure skater. You see the figure skater, they go into a spin and they start going rapidly around, faster and faster and faster. And then they'll kick a leg out, swing out their arms, they break their fast rotations. They have changed their moments of inertia. From this picture from left to right, this person has a high moment of inertia. This picture is high moment of inertia, high I. When they going this way to that one, they'll tuck their arms in, tuck their leg in. They are decreasing their moment of inertia. Well, to conserve angular momentum, if the moment of inertia decreases, the angular momentum increases. And so they start rotating rapidly around, faster and faster and faster. So, to demonstrate for you, I'm never content just describing a bunch of words. Let's go to the demonstration where I'll be the one rotating around like a fool for you.
So let's talk about these concepts of moment inertia, angular velocity, and angular momentum. When we say moment inertia, think of not just how massive something is, but how their mass is distributed, right? So in this case, I've got the barbell weights, and I've got them far away from my body. I have a high moment inertia. My mass is distributed outwards. Now I can tuck it in, reducing my moment inertia. My mass hasn't changed. I still have the same amount of mass, but I've redistributed where it is. Now let's give myself some angular velocity. Starting off with high moment inertia. So just give myself a little spin. Now I have some angular momentum, just some rotational momentum. I'm going to change my moment inertia, and I increase my speed. Slow down, speed up. Slow down, speed up. So, to conserve angular momentum, as I change my moment of inertia, my angular velocity changed as well.
Now I'm going to stay on this rotating platform, and instead of using those barbells, I'm going to grab this bike wheel and get this bike wheel spinning around. And now ask, what happens if I try to turn the wheel on its side? Right. Let's not hold any suspense, and let's just cut straight to the video.
In this demonstration, we're going to give the bike wheel some angular momentum, and then ask what happens when I try and change the orientation of the bike wheel. So with my feet planted safely on the ground, I'm going to give this nice good spin. Get a nice high amount of angular momentum. All right. Now let's twist this. What's happening? Let's go the other way. As I bring myself to a stop, if I change the orientation of the bike wheel, I change my angular momentum vector. So I have to start rotating to keep angular momentum conserved, the direction that this bike wheel initially had its momentum turning.
Let's be a bit more specific with our equations, and let's write down the angular momentum of a solid sphere. Now, this is not the angular momentum in all cases. This is very specific to, well, what we'll picture to be, say, our planets or our nebulous gas clouds, right? Just a uniform density. You'll have an object that's making a sphere of radius r, and it'll have some total mass lowercase m here. And it turns out that for this type of shape, the angular momentum of that object will just be 4/5 pi times however massive that object is, its radius squared, divided by the period, how much time it takes to go around once. Now let's go ahead and ask ourselves a question, harking back to our nebular hypothesis. If the radius is decreasing, remember gravity is causing this thing to collapse in on itself, what will happen to the period of rotation? We start off with this big rotating gas cloud, gravity acts on it, crushes it. What happens to the period? Go ahead and pause, figure out your answer, come right back. Let's look at the equation for angular momentum for this guy. All right. We say the angular momentum L has to be constant, has to be conserved. Well, 4/5 pi, numbers, they can't change. The mass. Is the mass changing at all? No. You've got this gas cloud that as the gas collapses down. Yes, it's getting denser, but the mass hasn't left the system. So the only thing left to change is the period. Well, if the radius decreases to keep L constant, the period must also decrease. Both of them have to change.
So here I have what's called a Hopman sphere. You might be familiar with these toys as they can collapse and expand and be fun to throw around each other. Now I set up a little string here so I can just pull on the string to collapse it. So now we're going to simulate our nebulas. We're going to give this a nice rotation. Start off rotating around, spinning, spinning. Now gravity acts in, brings this thing down, down, down. And it starts rotating faster and faster.
Related to the nebulas, we can talk about the Interstellar Cloud, which is just a denser than average region of space. Specifically, we call it the interstellar medium. So the interstellar medium is just the space between the stars. And you can talk about what kind of gases or dusters are there. And we have a interstellar cloud. Well, that's just going to be a denser region of gases, plasma, and dust. Whatever initial conditions were present in that interstellar cloud, it will be rotating around. It'll have some angular momentum. And there'll be this rotation axis. Every picture has this axis of which things are rotating about. Now, as you're rotating around, things that are rotating along this axis, they start to fall in. And that's just gravity. Look, gravity's pulling you in here, 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 here. Well, any material that's going this way, they have some inherent rotation trying to prevent them from falling in. Think of the ball and the string demos. Whereas this stuff that's rotating this way, they easily fall in and collapse. So this cloud will start to collapse down, and to conserve angular momentum, it has to start rotating faster. The result is this sphere of glass, this gas cloud, turning into this rotating disk, and we call it an accretion disk. So some further comments about this. Let's talk about the gravitational energy. Right? If I was to draw this line here, right, this line represents 0 gravitational energy. Now look at how much energy you have. Your gravitational energy is just defined by how far away from this red axis you have. So I'm a cloud that's a little dust particle here. I don't have a lot of gravitational energy. I'm pretty close to this rotation, all right, where this plane that everyone's going to fall into. Whereas I'm a gas cloud up here, if I'm a little dust here, I have this great big fall to go through. So this material has high gravitational energy, and when it collapses, falls down, well, That's going to create the hottest objects. This high gravitational energy has turned into kinetic thermal energy, making this hot centered region. So the parts in the center will be the hottest. And as you go further out, there's less gravitational energy being converted into rotational and thermal energies. So tying this all together, at the end of this process, we'll have an accretion disk. And that accretion disk is growing bigger and bigger because material has fallen into it.